We've got a problem here where they're asking us to find the limit as x approaches 2 of 1 over x minus 2 squared. What we're looking at here is an overall limit. So there's no plus minus in the exponent on that 2. So we're looking at an overall limit on this problem. I always tell people option 1 for me on any limit problem is I always just try plugging that value in. So whatever x value I'm approaching, in this situation 2, I go ahead and just try to plug it in. You would be surprised how many times option 1 works, and it's always worth plugging it in. So I'm going to take that 2, and everywhere I see an x in this equation, I'm just plugging in that 2. So I get 2 minus 2 squared. Here, it doesn't work out for us. We end up with 1 over 2 minus 2 is 0, and 0 squared is 0. So we end up with division by 0, which is the biggest no-no in all of math, right? So we can't work with option 1. We're now on to looking at our other options. And as you scroll through your standard options, factor and cancel, that's not going to work here. This isn't a complex fraction or absolute values. And so when that happens, most of the time what you're looking at is probably a vertical asymptote, but it really leaves us to the last game available to us, which is what I just call the big small game. So the big small game has us kind of working in a more conceptual way with this limit. It's not going to be as algebraic as all the other methods, so not everybody's favorite thing, but we can get it done. When we go to find an overall limit, remind yourself that an overall limit is always got to be answered by finding what the left-hand limit equals, and then again finding what the right-hand limit equals, and seeing if those two values are the same. So even in this situation, that's where we want to default to. So if it's an overall limit, what's the left-hand limit look like, and what's the right-hand limit look like? So we're really breaking it into two smaller problems now. So I have limit as x approaches 2 from the left this time of 1 over x minus 2 squared, and then I set up the other limit. We've got limit as x approaches 2 from the right of that same exact equation. And we'll calculate these out and see what we get. When we go to play the big small game, looking at the left-hand limit, we're basically doing a modified version of option 1. We're going to choose an x value to plug into our equation here. We just need an x value that's really close to 2 from the left. If you think about this in terms of a number line, if I put 2 right here, coming at 2 from the left, you can see that numbers really close to that would be something like 1.999999999, right? A 1 with a whole bunch of 0.9s behind it. And so that's what we're going to plug in, sort of our option 1 on this problem here. And it's going to kind of help us see conceptually what's going on. So we've got limit x minus 2 squared, and now we go ahead and plug that 1.999 in for x. So we're looking at 1.99999, a whole bunch of 9s, minus 2, and then squared. What you're going to want to do is you sort of work your way through this and kind of clean it up and see what you have. On top, we've just got this positive 1 going on, so nothing exciting there. On the bottom, we have 1.9999999 minus 2. 1.99999, no matter how many 9s we put on that, that's always going to be smaller than 2. So we may not know much, but we know that this is going to be a negative number, and it's going to be a decimal point with a ton of zeros, right? Sort of mentally, that's what we're getting out here, and that whole thing's going to be squared. Looking at this, well, if I square a decimal on the bottom, right, we're just kind of conceptually continuing to work this thing out. We get a positive 1 on top, and then squaring a really small number is going to end up, anytime you square something, it's going to be a positive. And then that number, those decimals are going to be even more decimals going on the bottom here, right? So now we come back and say, well, what does that mean? What it means is on the top, I have a positive 1. So positive 1 is really like a very big number compared to all these decimals. So we've got a positive big on top. And it's on the bottom, we are dividing by a positive small number. So looking back at the line above, you can see that a big number divided by a really small number becomes something huge. If you put that into your calculator, it's going to give you scientific notation, 1 times 10 to the 35th, which is a huge number. And so huge in math speak means infinity. So we know we're headed to an infinity, and what we always have to do is sort of reconcile our signs at the end. We have a positive over a positive, so two positives give us a positive. So from the left-hand side, the limit as x approaches 2 from the left, we are getting positive infinity. And we know right now that no matter what, we definitely have a vertical asymptote because we only need one of these limits to come through as infinity for there to be a vertical asymptote at that value. Now the real question comes in is, does the right-hand limit equal the left-hand limit? We got to answer our real question, which is, what's the overall limit here? So we go back and we play that same game now with our right-hand limit, the same little mental game. This time, as we're coming at 2 from the right, we're really thinking about plugging in a number like 2.0000001, right? A 2 with a whole bunch of zeros and then a 1. So when I plug that into this equation for x up inside here, I look at it. So this is x minus 2 squared. We're looking at 1 over 2.000, right? A whole bunch of zeros and a 1, and then that minus 2. So now we decipher it again. You know, the work that I'm showing you here to decipher this, the more you do of these, you know, the more that you'll kind of just be able to mentally do in your head. But as we work it out together here, we'll kind of go through it all. So this on top, we still just have a positive 1 sitting up there. On the bottom now, 2.0001, 2.00001 is always going to be bigger ever so slightly than 2. So what we know is we're going to have a positive and then a decimal point with a ton of zeros and a 1 squared. Then just like we saw on that other example, you know, when we square the bottom of this thing, we're going to end up with an even bigger decimal, right? An even smaller number squared, and we actually just squared, so we don't need to square again. We'd end up with a positive value out here because we're squaring. So no matter what, you always end up with a positive when you're squaring. And now we play our little big small game here to kind of decipher this out. So on top, I've got a positive big divided by on the bottom a positive small. And so anytime we've got a big number divided by a small number, the result of that is always going to be huge. The smaller that number gets, the bigger the outcome's going to be. And so what we call huge in math speak, right, is infinity. And again, you reconcile your symbols over here, so your signs. So we have a positive over a positive. Two positives are going to end up giving us a positive infinity. So we already knew we had a vertical asymptote, but if this side was the only one equaling infinity, we'd know it even more now. So we have a left-hand limit that's equal to positive infinity, a right-hand limit that's equal to positive infinity. And so now we compare these two. And this time we see that those two things are equal. The left-hand limit equaled the right-hand limit, which equals positive infinity. And so that tells us that our overall limit that we were trying to get equals the exact same value. So in this situation, the limit as x approaches 2 of 1 over x minus 2 squared is going to be headed to positive infinity. We also know, concluding here, is that we have a vertical asymptote. Whenever one of your limits, a left-hand limit or a right-hand limit, equals infinity, you know you've got a vertical asymptote. That's what you've proven here. And so we know we have a vertical asymptote at the x value we cared about. So we have a vertical asymptote at x equals